last topic here is the biological effects of radiation. So why is it scary to be exposed to radiation? Well, we're exposed to radiation all the time. It's just the dosage, right? Everything is fine in moderation. It really just depends on dosage. So radiation sources in the natural atmosphere. We ingest foods that have radioactive materials in them. So potassium 40s in bananas. The air has radon 222, and the ground is uranium 238. So we are always exposed to radiation. We have man-made sources. So X-rays have certain amounts of radiation, which is why your X-ray tech is always going to leave the room, because otherwise they would be exposed to radiation on a regular basis, which is not great. We use it in medicine. It's in air travel, it's in cigarettes. There's radiation all over the place. Okay. Now the average background radiation is about 360 millirem. And that is what we use to calculate dosage. So 360 millirem obviously is going to be fine because that's what we live with every day. Okay, but if you're exposed to more of any of these things, that could potentially be a problem. So we have to measure our dosage, especially if you're something like an X-ray tech. Okay, so what do these do? So essentially radiation can cause ionization, right? Ionization means things turn into ions, right? So this is called ionizing radiation. So when a molecule absorbs radiation, like a gamma ray, they can lose electrons. Okay, so this is an example of water being radiated. Okay. If it absorbs that radiation, it loses an electron, turns into H2O plus. So that's a weird looking molecule, right? And that can react with another water and get H3O plus. That's familiar. That looks like an acid molecule, and a free radical. There are those fun free radicals again. Highly reactive. So if you have free radicals in your body, we got water, a lot of water in our body, and if it reacts with radiation, we get these free radicals. Those will start to break down all kinds of stuff and cause havoc on your system. So this is just one reaction that can potentially happen if you're exposed to radiation. And like I said, those free radicals are highly reactive. They will react with things that they shouldn't. So we have to watch our dose. Okay, so how do we calculate radiation dosage? Well, the first thing I want to talk about is RAD. That is the radiation absorbed dose. So like per your body. So we measure this, it's 1 × 10⁻² joules per kilogram of body tissue. Okay, this is a constant, it's on your equation sheet. That's the RAD. Now, certain types of radiation are worse than others. Okay, we've talked about all these decay types. And the way that we differentiate these is called the RBE. So this is just a value, excuse me, that you multiply the RAD by to figure out how bad your dosage is. Okay, so a multiplier depends on the particles. So beta and gamma are, the RBE is just 1. Okay, so beta and gamma are not as bad. You can absorb more of that than you can an alpha. Now, alpha can get through your skin, but if you ingest alpha, it is 10 times worse than beta and gamma. So if I want to calculate my REM, excuse me, or my millirem, I said before, right? That's how we calculate, that's the dose. You just do this value times the multiplier, right? So it's like how much you were exposed to. That's how we calculate our dose. It is dependent on the type of decay you're exposed to, or type of radiation, sorry, that you are exposed to. So which ones are worse and why? We're going to specifically talk about alpha, beta, and gamma, because whenever we have these reactions, these are the radioactive particles that can hurt you. Now, alpha is the least penetrating. So we use penetration to tell how far it can get through you or other things. Alpha can't get through much. Okay, your skin actually will block you from absorbing alpha, which is good. However, if you were to ingest it in any way, so if a bomb went off and alpha radiation was in the air, if you ingested it, it damages your soft tissues and that can cause you to die. Okay, beta and gamma can actually get through your skin. So beta can just go through a couple layers of skin. I'll tell you what we kind of use beta for in a minute, but beta can actually get through your skin, and gamma can go all the way through. You can even go through sheets of lead. So it is the most penetrating capability. So these, while not as bad, you can take a higher dose of them, they can actually go through you. So that's why gamma rays are so bad and they're so tiny. They can actually disrupt and break down DNA molecules, which cause mutations, which is not great. So all of these are bad, but in different ways. Okay, so these ones mostly affect tissues that reproduce rapidly, meaning your skin, your bone marrow, intestinal lining, things that reproduce cells a lot are going to be very damaged by alpha, beta, and gamma. Now we can use these, we use them in medical applications a lot, for diagnosis or for therapy. So diagnosis, these are some examples of radioisotopes that we use to actually, in medicine. So diagnosis wise, we always start with, we use a very low dose, and things that have short half-lives. So they're going to break down really fast and get out of your system. So you don't have a bunch of radiation running through your system. And so for diagnosis, essentially what you do is you inject it into the body if wherever you need to like highlight what we're looking at. And it illuminates that targeted area. So I'm going to use iodine as an example because we actually use these a lot. Iodine 131 to diagnose. They will put iodine into your body because that actually gets processed in the thyroid. So what happens is the iodine then, because of bodily systems and how they work, gets transported to the thyroid, and then it's going to release that radiation, and we can actually detect then what is going on. We can get a picture because it gets through your skin of what's going on in your thyroid to see what the problem is. But it has a quick half-life, so it's going to get out of your system pretty quickly. And so it kind of gives off that radiation. We read that radiation and we know what's going on. So it's kind of how we use it for diagnosis. For therapy, so this would be like a cancer treatment. We use really high doses, but again, short half-life. We don't want it to be in the system for a long time. So we target those tumor cells and we try to essentially kill them with radiation. Radiation kills our cells, right? It's just that we try to target those cancer cells. Cobalt-60 is one used a lot, phosphorus-32. Those give off radiation that can actually kill those cancer cells. Okay, half-life, phosphorus-32's half-life is really short. Cobalt-60, it's 5 years, which is kind of long, but in the grand scheme of things, if it can target those cancerous cells, then that's going to be really great.